We've spent a lot of time over the last few sessions really embedding ourselves in the fundamentals, the world of Git, commits, merges, version control.
The foundation is the necessary groundwork for managing code history.
And now we make that a critical shift. We're moving from just storing code passively.
To active, automated engineering.
Right.
This is the moment where version control really becomes a full CI/CD platform.
Exactly. We're talking about full automation, continuous integration, continuous delivery. So the code is saved, and then this whole cascade of automated actions just follows. Testing, security scanning, building, deploying.
But all that magic needs a brain, a central controller.
And that central critical control panel is a single file living right in your repository called .gitlab-ci.iml.
This file is the driver of the entire pipeline. It really is. It's the manifest of your intent.
Yeah.
When you push code, GitLab looks for this one file, reads its instructions.
And hands those marching orders off to the system workers. And those workers are the GitLab runners, right? Just so you, our listener, are perfectly clear. What exactly is the runner doing here?
Think of the runner as the engine. It's a dedicated, isolated virtual machine or container that is just waiting for jobs from your project.
Waiting for orders.
Exactly. When the .gitlab-ci.iml file says run the unit tests, the runner is the one that actually boots up, executes those commands, captures the output, and reports back to GitLab whether the job passed or failed.
So our mission today is really the shortcut. We want to cut through the YAML syntax jungle and help you understand the core structure and power of this configuration file. We want you to stop seeing it as just another text file.
And start seeing it as the orchestration score for your entire DevOps process. It's the key that unlocks the whole platform. So yeah, let's unpack this crucial blueprint.
Okay, let's do it. So when you first open this file, what are the two primary building blocks, the foundational concepts we have to understand to decode the whole pipeline?
The pipeline is fundamentally built around stages and jobs. Stages are the high-level sequence of actions. They define the major milestones and, critically, the order in which we attempt them.
And what's the defining characteristic of a stage? I mean, I know the common examples are things like build, test, deploy, but what's the architectural rule here?
The key rule governing stages is that they run strictly sequentially. Stage 1 must fully complete and, more importantly, succeed before Stage 2 can even begin.
Not just a suggestion, then. It's a hard stop.
It's a hard architectural bottleneck, and it's built for safety and for resource management.
So why the hard stop? Why can't I start my unit testing while, the last few files are still compiling in the build stage? Is that just a technical limitation, or is it a strategic choice?
It's absolutely a strategic choice, and it's designed for efficiency. Think about it. If your build stage fails, maybe a syntax error, a dependency mismatch, do you want to waste time and expensive runner minutes trying to run the test stage?
Of course not. The test would fail anyway.
Absolutely not. So the sequential nature means if that first stage fails, the entire pipeline stops immediately. You get instant feedback, and you save resources that would otherwise be spent on, well, completely irrelevant downstream steps.
That's the critical insight. So stages impose order and enforce safety. They define those major steps like build first, then test, then deploy.
Precisely. Now, within those sequential stages, we define the jobs.
And the jobs are the actual work.
Yes. Jobs are the actual tasks that get executed, the commands, the scripts. You might define a Unix job, a linter job, or a compiled binary job.
And this is where we get that huge time-saving feature, right? Because while stages are strictly sequential,
jobs within the same stage are not.
They run at the same time.
That's right. By default, jobs defined within the same stage run concurrently in parallel on separate runners, if they're available. This is how you reclaim hours of development time.
That parallelism is just huge for speed. You can picture it, right? You define your sequence stages.
Yeah.
Build, test, deploy. The system makes sure build finishes before test even starts. But once that test stage activates, you can define your Unix job, your integration test job, maybe security scan job.
And they all fire off simultaneously, dramatically cutting your overall testing time.
And you can take that even further, can't you?
Yeah.
Let's say you're dealing with complex matrix testing your app across 5 different versions of an OS or 5 different browsers.
Oh, that's a perfect use case. You can just define 5 separate jobs in that test stage, one for each environment. All 5 will run at the exact same time. You get your feedback in minutes instead of waiting for hours.
That makes perfect sense for optimization. But okay, whether we're running sequentially or concurrently, every single job has to execute a command. What's the one fundamental keyword that ties a job definition to the actual work it needs to do?
That would be the most fundamental keyword of all: script. Every single job definition requires the script. Keyword.
And that's just a list of commands.
A list of shell commands, plain old bash or whatever shell your runner's using, that the runner will execute. You might list commands like npm install or go build or pytest tests. This is the core instruction set for the automation.
Okay, so we have the structure, sequential stages containing concurrent jobs, all driven by that simple script keyword. But let's get into the command center and talk about the environment, because if I tell a runner to run go build, how do I know that runner even has go installed?
Yes. And this brings us to that crucial practical problem of environment management.
The classic "it works on my machine" problem.
That is the core challenge solved by modern CI/CD, and we solve it by using the image keyword.
The image keyword, which points to a Docker container.
Correct. When you specify, say, image.node.18alpine at the top of your job definition, you are telling the GitLab runner, before you run any scripts, go pull this specific Docker image and execute all my commands inside that isolated standardized container.
That is so elegant. It completely decouples my code's requirements from whatever is running on the actual GitLab runner machine itself.
Completely. If your local machine uses Node 20, but the project requires Node 18 for stability, the CI pipeline will automatically use the correct version, guaranteeing consistency every single time.
It ensures the build process is repeatable, predictable.
Every single time, regardless of what else is running on the underlying hardware.
Fantastic. So environment managed. But we immediately hit the next big practical challenge. We said stages are isolated. They're often running on separate runners and separate Docker images. So if my first stage, the build stage, compiles a massive binary file, how does the test stage, which might run 10 minutes later on a completely different machine, access that output?
And this is where it gets really interesting. This is where the CI/CD pipeline starts to feel less like a script and more like a full orchestration platform. We use the artifacts keyword.
Facts.
Artifacts are essentially files or directories that are generated by a job.
Yeah.
GitLab temporarily stores them in the cloud after the job completes.
So it's not just a file transfer. It's more like a dedicated, version-controlled courier service for build outputs between the pipeline steps.
That's a great way to put it. Artifacts serve two critical functions. First, as you identified, they're used for passing data. Any files you define as artifacts in the build job are automatically uploaded, stored, and then seamlessly downloaded into the workspace of the jobs in the next stages.
So that immediately solves the build output to test input problem. If the binary is an artifact of the build, the test job just finds it waiting there in its working directory.
Absolutely. The second critical function is availability. Sometimes a job generates output. You don't necessarily need to pass downstream, but you need to keep it for review or debugging.
Like test coverage reports or security scan results.
Exactly. So the developer doesn't have to SSH into some random server or dig through complex logs. The report is just a click away on the GitLab interface associated directly with that commit and that specific pipeline run.
Okay, so when we define artifacts, what are the key parameters we need to worry about? I imagine storage isn't unlimited.
It is not. That's the key technical detail. You must define the path. That's the specific files or directories you want to save. A common mistake here is using the wrong relative path. It's always relative to the job's working directory.
That's a great practical tip. Where the path starts from matters.
It matters deeply. And because storage isn't free, we use the strategic optional parameter, expiring. You might say expiring 1 week or even 1 day. This automatically deletes those stored files after that period, which is essential for managing storage costs.
Especially if you have hundreds of pipelines running daily, each one generating gigs of data.
You have to clean it up.
So artifacts are the mechanism for state management across these isolated, stateless jobs, and expiring. Gives us budget control. It's all about efficiency. Which brings us to the final, and maybe the most powerful feature, precision control over when things run.
Ah, yes, selective execution. This connects to the bigger picture. Every job consumes resources. Runner time, network bandwidth, storage. Some jobs are expensive or carry inherent risk, like deploying to production.
You definitely don't want that running by accident.
Absolutely not. So we need the ability to control when a job runs to save time, money, and reduce that operational risk.
Let's take the most common scenario. We only want that high-risk, expensive deploy-to-production job to run when changes are pushed to the main branch, a stable release. We do not want it running every time a developer commits to their feature branch. How do we draw that line in the YAML?
You use the only keyword. This makes a specific job run only when changes are pushed to the specified branches or tags. So on your deployment job, you would simply add only main.
And that's it.
That's it. If a commit comes from a branch called feature X, the runner sees that only main rule and just says, nope, not running this one, and skips it.
Simple, effective control for risk mitigation. You prevent accidental deployments just by checking the branch name.
Now, consider the flip side. Let's say I have a very quick pre-commit style linting test. It gives instant feedback to developers. I want it to run on every feature branch, but I don't want it to run on main.
Why not on main?
Because main runs a different, exhaustive, hour-long compliance and security scanning suite that runs on a schedule. The little linter is redundant there.
So we want to run everywhere except the primary branch.
That's where you use except. This runs the job for every branch except the ones you list. So you would define that fast linting job with except main. It runs across all your development branches, giving that fast feedback, but you avoid redundant checks on the main branch.
It's a great mechanism for managing complexity. Feature branches get fast, lightweight feedback, while production paths get the full, rigorous treatment. You're using branch naming as an essential configuration tool.
And you can get really sophisticated. You can use predefined variables in these roles, letting you create dynamic controls based on the environment.
And this all loops back to our foundational Git knowledge, doesn't it? The crucial final step is remembering that for any of this to work, the .gitlab-aci.iml file itself has to be version controlled.
It has to be.
It needs to be committed and pushed to the repository. The automation only starts once its instructions are part of the codebase. That ensures the rules for automation are as auditable and traceable as the code they're processing.
It creates this beautiful cycle of self-regulation. The automation governs the code, and the code governs the automation.
So what does this all mean for you, the learner? We took a deep dive into the engine room here. Let's just synthesize how these concepts, stages, jobs, artifacts, and control work together.
Okay. The problem is reliable, rapid software release. The solution, driven by this one file, orchestrates the entire process.
We establish the order and safety with sequential stages: build, test, deploy.
Within those stages, we achieve speed by using concurrent jobs, often specifying a precise environment using the image keyword to guarantee repeatability.
We manage communication and state between those isolated jobs using artifacts to pass those crucial compiled files downstream.
Ensuring the test job sees the binary the build job created.
And finally, we enforce control and resource efficiency by using only or except to make sure those expensive or critical tasks only run on the right branches.
Exactly.
Mastering this one configuration file really is the essential key to transforming your development workflow. You're turning tedious manual tasks into reliable, repeatable, efficient processes.
It fundamentally changes your view of version control. It stops being just a storage system for code history, and it transforms into a full, intelligent orchestration engine. Every single commit is not just a backup, it becomes an opportunity to trigger immediate, automated, and intelligent action. That, right there, is the power of CI/CD.
And that's it for this deep dive. Thanks for joining us.
We'll see you next time as we continue our CI/CD series.